All right, let's talk about pi bonds and polarizability. So if you have a pi bond, and it's going to be a little interesting because the more of these double bonds, triple bonds, etc. that you have, usually it's going to increase polarizability. So electrons in the pi bonds are a lot more delocalized. Because they're more delocalized, they're going to be able to move around and create more polarity, which means that they become stronger. So keep that in mind whenever we're talking about, pi bonds for that. All right, so let's talk about the force of attraction and how strong these forces are going to be. An ion is going to be your strongest, and we already know that because salt, as an example, is a crystal. It has one of the largest, if not most strongest structures because, again, it has that ability to have those attractions. Second comes in is ion dipole. An ion dipole, we've already talked about this, when you have water and a salt molecule surrounding that, it creates that electrostatic charge. Now, a hydrogen bond is a small molecule. It can have really strong, it's one of the stronger ones too. It's like coming in third. It has strong intermolecular attractions when the H bonds are present. Then we've got things like the dipole-dipole, which come in second. Fourth, ion-induced dipole, dipole-induced dipole, and London dispersion forces. And often the strongest force of attraction between the large species. So usually larger molecules generally have London dispersion forces. And usually what you'll see is dipole-induced dipole, dipole-dipole, etc. But London dispersions are going to be by far the lowest ones, which apply to all of them. Alright, so let's go ahead and explain which species has the higher boiling point. C2H6 or C3H8. Now, in both cases, they are both polar. And so if you analyze these right here, you can automatically see that the electronegativity for carbon and hydrogen is very low. So what happens there, it creates a non-polar region. Now, the larger molecule has the higher boiling point. And the reason why is because those atoms, since they're a lot larger, they have more electrons, they become more polarizable. And so only London dispersion forces are going to act on these molecules since they both have kind of like the similar sizes, since you got carbon and hydrogen. And so the boiling point for these are going to be 89 and negative 42. So the question is, why would this one, the C3H8, have a lower boiling point, a higher boiling point than this one? And the reason why is because it just has a larger mass. C3H8 has a larger mass than C2H6. Alright, next question is, which species has the higher boiling point? Identify the IMF forces acting on each. And so the answer here is quite simple. If you take a look at CH3CH2OH versus C3H8, what you're really looking for is what type of IMF force you've got in this situation. So we've already identified this as being a polar molecule, and this right here being a non-polar molecule. And the reason why we identify that is because of the OH region right here next to the carbon. And this creates a very interesting phenomenon because if you talk about polarity, you're talking about strength of atoms, we begin to see that we have two types of forces. One, the hydrogen bond indicated here by the OH. Here we don't have that. But here we have London dispersion forces because they're induced dipoles, and we also have dipole-dipole interactions. Here we only have London dispersion force. So the obvious answer is this one would have a higher boiling point because it has the extra H bonds. In this case, it has a boiling point experimentally of 78 degrees Celsius, while your C3H8 has a negative 42 degrees Celsius. Alright, let's try to see if you can pause this one and see if you can do it yourself. This one has which species has the higher boiling point and identify the IMF on each one. So if I take a look at CH3OH versus CH3CHOH, CH2OH, we automatically know a couple of things. So the first thing is both are going to be polar. So if you take a look at OH here, you automatically can tell that because they have that OH, it's going to have that tug on that electron, creating that polar molecule. We also identify a hydrogen bond right here as an OH, and that's going to be considered a London dispersion force. In this specific case, we can also see that this is going to be considered a London dispersion force. And because of that, you're going to have that situation where because we have that OH molecule, these two are going to be polar. The left one is going to have is a smaller molecule and is less polarizable, while the one on the right is larger and it has more polarizable. And because it's a larger molecule, its boiling point is going to be at 188. So all things equal, polar basically are going to have this idea that if they're both the same polarity, the one with the larger molecule is going to have a higher boiling point. Alright, question here is which one has a higher melting point? Identify the IMF forces acting on each. So let's take a look at CH4 and CI4. So obviously we can tell that CH4 automatically looks like a nonpolar molecule. The CI4 also is a nonpolar just because of the fact that it actually has a symmetrical shape. So if I'm looking at this and I draw the Lewis dot structure, I can see that it actually has 1, 2, 3, 4 attached, 1, 2, 3, 4 attached, and it has both polar regions. If these were two solids and I want to melt them down, question is, what would create that? What's the prediction for the melting point? Because they're both nonpolar, I can automatically assume that they have London dispersion forces for both intermolecular forces. There wouldn't be any sort of hydrogen bonds because we don't have highly electronegative elements. And so because of that, this is going to be a much smaller molecule because if we take a look at the molar mass for that, that's about 12 plus 4, which is 16, while iodine is a much heavier molecule. And that gives you a much more larger but more polarizable one. And we find out that CH4, which is methane, has negative 183, and CI4 experimentally proves that it's 171. So it's a very interesting idea in terms of that. Okay, let's take a look, see if you can do this one. This one's going to be which one has a higher melting point and identify the IMF for each one. So NaCl is obviously going to be, go ahead and pause the video and see if you can do it yourself, and versus water. So this one's going to be ionic and water is going to be H2O, which is going to be polar. And as you can see from here, because it's an ionic one, we automatically know that it has one of the strongest forces. And because of that, this is going to be an ionic bond. While H2O is considered to have a hydrogen bond and also London dispersion. So again, London dispersion can apply to this. Normally we wouldn't write a London dispersion force for the ion because of the fact. Moving down the line, we always see that the boiling point for sodium chloride is 1,413, amazing, while the boiling point for water is 100 degrees Celsius. So that gives us a very interesting situation here because normally you would find that water has a much higher boiling point, but because it has those London dispersion forces, it goes up to 100. So again, looking at the bond's strengths. Okay, let's talk a little about biomolecules and the application to biology. So normally when you see biomolecules like this, they usually construct things like polymers, and usually you'll see them in amino acids specifically when you're trying to build proteins. And so here's an example of an amino acid structure where it's strung along in these chains. And if you remember from biology, what we usually have here are these single bonded atoms that bond together, and because they form these nitrogen atoms, they will actually create these long chains. And so the question here is, are there any sort of hydrogen bonds that exist between these? And the answer is absolutely. The hydrogen bonds are forming between the oxygen and the hydrogens. So if I take oxygen from one side, it can actually interconnect to that. And because of that, you're able to form these secondary structural protein molecules. An example of this is called an alpha helix. An alpha helix is a protein molecule that arranges itself in such a way to create a specific pattern. And so if you think about protein molecules, they are so interesting because with these different protein molecules, they can interact differently in your body and produce different effects. This is actually a beta pleated sheet and is held together by these hydrogen bonds. But notice carefully the shape, is a little different. So the protein molecules are going to form these secondary structures. When they form these secondary structures, what they're going to do is create brand new proteins that maybe the cell has never encountered before. A tertiary structure is caused by intermolecular forces between the R groups. And so again, taking a look at hydrogen bonds, London dispersion forces, you can see all the different possibilities and combinations that you can create because of these intermolecular forces. And so one of the applications of protein synthesis and pharmaceutical companies is to generate new proteins that are going to be able to solve some of the new diseases and cure some of these diseases in the world. And by understanding these London dispersion forces and hydrogen bonds, you're going to be able to cure many of these diseases that are found everywhere. All right, guys. Well, hopefully you enjoyed everything for intermolecular force. Again, just kind of go back again, pause the video, watch it one more time to kind of get an idea for how these forces interact. Why is it that they're interacting with each other, and what actually causes these forces to exist?